Hi, my name is Skylar.
And my name is Xander, and we did our project on velocity and acceleration.
Go.
Alright, so on the left here we have a table of the data recorded from Skylar's particle running, along with the distances on the right. And this roughly equates to 12 cosine of x. And we've graphed the points, and we're just going to graph them together here. And it comes out to something roughly like this. Excuse my bad drawing. And so now that we have our position function, what we'll want to do is find our velocity function, which we'll call v of x here. And we can find v of x by taking the derivative of y, our position function, and that'll be equal to negative 12 sine of x. Our next step is then to find the acceleration function, which we'll call a of x, which is equal to the derivative of our velocity function v of x. And this will be equal to negative 12 cosine of x. Alright, so now we're going to work backwards to check our answers. So from a of x, we're going to find our velocity function again, but this time we're going to do it by integrating our acceleration function a of x, and this will give us, oh, don't forget about that dx, and this will give us negative 12 sine of x, and then our initial condition for velocity at x equals 0 will be 0. Don't forget about that constant of integration plus c. Now in order to find what c is, we're going to set that equal to 0. So we get c equals negative 12 sine of 0, and we figure out that c equals 0. Now we're going to find our position function, check our work once again, by taking the integral of our velocity function and using the initial condition that our position function at 0 equals 12. So the integral equals 12 cosine of x plus c, and we're going to set 12 cosine of x plus c equal to 12. Sorry, cosine of 0 plus c equal to 12. And this will give us 12 plus c equals 12, figuring out that c should equal 0. Now, a generic problem like this will ask us to find one of these types of data at a certain point. So we'll go ahead and do that for point 0 for all of these equations. So I copied all the equations that we have down here from above, and we're going to find position at 0 equals 12 cosine of 0, which is equal to 12 because cosine at 0 is 1. Velocity at 0, at time 0, is going to equal negative 12 sine of 0, and we'll find out that that is just equal to 0 because sine of 0 is 0. And then finally, acceleration at time 0 is negative 12 cosine of 0, which is negative 12, again, because cosine of 0 is 1. So now we're just going to do some graph analyzation here. I brought down the answers from the last problem, and we can see that position is 12 because this is a graph of position, and it's at 12 at 0. We know that we can see velocity is 0 because it has a horizontal tangent line there. And the way we see that acceleration is negative 12 is because it's less than 0, which means it's concave down, which we can see. The graph is concave down because it looks like a sad face.
3, 2, 1, allez!
Welcome to analyzing the Xander particle. Alright, so let's get right into it. So, here are the times that we got for Xander, and you see them all right here. And so, we can get that equation, x minus 2.89 to the third. Alright, so, letter A. Let's graph it. Alright. So, let's see, negative 2.89. So, that's going to represent our h. So, we're going to put that right there. In between 2 and 3, we're going to put that right there. That's around 2.89. And so, with a 3, that is a cubic function. So, it's going to look, let me change my pen a little bit. It's going to look about like this right here. It's going to look like look like that. Alright, so let's draw this. We'll start at about 1, and we'll go flat here and right up. Oh, my pen did a little something weird. Whatever, it's alright. We get the gist of it. We get what we need. Alright. So that's letter A, that's graph. It doesn't look too pretty, but right there is 2.89, comma 0. And that's what our graph should look like. Alright, find the position of particle at t equals 3. So what we're going to do is a little nice substitution right there. So we're going to set up the equation, substitute 3. So that'll be 3 minus 2.89 cubed. So we're just going to use we're going to calculate that. 3 minus 2.89, 0.11 to the third. And then we're going to use our calculator, and we're going to find that this equation is equal to 0.001331. Alright, now let's check that with our graph. Alright, we can look. Let's see what we have on 3. That looks pretty close. See, 1's right there. So that's 0.001331. Oh, the pen did a little something weird again. Alright, so that's good. We checked it. Alright, now on to part C. Calculate the velocity at t equals 1. Alright, let's start. Let's define what velocity is. Velocity, we're going to define that as z prime of t. Because, yeah, velocity is z prime of t. So, what we do, we're gonna find the derivative. So, 3x minus 2.89 squared. And then we have to find the u substitution, although this is just basically a simple x, so u prime is just going to equal 1, but we still have to use chain rule because it's in parentheses. So we're just going to multiply that by 1. There, okay, there we go, we got the 1 there. So now we're going to simplify this, just take away the 1 basically, so 3 times, the little message from my friend here, we're going a little bit late, x minus 2.89. 2.89, there we go. And squared. So, we have to find this at t equals 1. So, let's v of 1, t equals 1, yeah, v of 1 equals 1 minus 2.89 squared. So, let's read this. 3 times negative 1.89. That's just quick math for you. I'm very smart. And we're going to use our calculator now. 3, negative 1.89 squared. And that is going to get us around 10.7. In what direction is this particle traveling? Alright, so, since v of t, v of 1, I didn't change that. I should change that. Let's fix that. Particle is, oh, there we go. Particle travels to the right. So this would usually be true. But since we recorded Xander walking in a different way, because we did that, it's actually going to go to the left. But usually, if we're looking at the graph, it would be going positive towards the right. The velocity, the particle will be going positive towards the right. So, if we reference the graph, then go to the right. But if we reference the video, it would be going to the left. but just know it's traveling in a positive direction towards that 12. All right, letter D. Is the particle speeding up or slowing down at t equals 1? Justify your answer. So what we need to do, speeding up, slowing down, we need to compare acceleration of t and, oh, no, let me redo that, and velocity of t. We need to do this so we see if they work together or they counteract. So let's define A of t. A of t, this is, like I said before, it's the acceleration. Oh, let me get that a little bit better spelling for you. Acceleration. So that is going to equal v derivative, the derivative of velocity. So let's do what we did for part C. So, okay, 6 times x minus 2.89, and since we brought the 2 down, we're just going to have a 1 there. And then let's use our u substitution for chain rule. That's just going to equal 1 because we have the same parentheses. So basically what we're going to get is 6 times x minus 2.89. And if you want to be fancy, you can multiply that out, but that's not necessary for this equation. It's actually going to be very much easier if we keep it the other way. Okay, a to 1 is 6, 1 minus, no, not 1, 2, well, alright, to 1.89, and, oh, wait, let me change that really quickly. Yeah, there we go, 2.89. I was getting a little bit mixed up from earlier. Alright, so what we're going to do is 6, 1.89, so let's plug that in, and we get negative 11.34. So, now let's compare the two. Let's see if they have the same signs. So, negative 11.34, negative, oh, sorry, let me get that better for you, negative 11.34, and 10.716, and 10.716, So, this is going to be slowing. These signs are two different signs. So, since hit my keyboard there for a second. Let me scroll back up. Since these signs they don't match. Since the signs don't match, the particle Xander is slowing down at t equals 1. Because acceleration a of t and velocity v of t are working against each other. They're fighting each other because one's going slower, one's going faster. So the particle is overall slowing down. Alright, that is it for my section. We have fully analyzed particle Xander. Alright, I hope this all made sense to you. I feel like I went through it pretty well, so I hope it makes sense to you. Bye.
Now you may be wondering, why does this work? Why are we able to take the derivative of a position function or a velocity function and get the next step up? Well, to answer that, we first have to think about what is a derivative. A derivative is the rate of change of a function. And what is velocity to position? It's the rate of change of position. It's measured in meters, which is a distance measurement per second, and seconds is time. It's a rate that we measure things by. And if we also want to think about why this works going backwards from acceleration back to velocity or back to a position function, is because an integral is the opposite of a derivative.